Hi, everybody. Let's start off with a few quick questions. Please raise your hand if you're using an Android phone. Oh my God, that's so many of you. Now, please raise your hand, all the iPhone users. Cool. What about the rest of you? Any Nokia, BlackBerry, Windows Phone users at the audience? No, no one? Okay. So now, can you please raise your hand if you're using Face ID or whatever the name of the equivalent Android technology is? Cool, keep your hands up, and that's the interesting part. If you think that your face is a better, more secure login mechanism than the old entering a few digit passcode. Okay, thank you very much. My name is Roy. I'm a security software engineer at Own Backup. By the way, we have a booth just downstairs. Feel free to come by, say hi, maybe hear about some job opportunities. And I don't know about you, but when I got this question at first, I thought to myself, that's a no-brainer. Of course my face is more secure than a short combination of a few numbers. Well, I see that most of you are skeptic about it, so now you really have to stick around until the end of the presentation. I promise you some really interesting results. Let's get a couple of years back, down in memory lane. I still remember when my dad bought his first iPhone 3G. A pretty dumb smartphone by today's standard, but for me as a child who was fascinated by technology, that was something else, something from a science fiction movie. And I remember messing around with it, downloading some apps, playing Angry Birds. And I remember this one app that promised I will be able to unlock my phone only using my finger. All you had to do is put your finger on a screen, a cool animation of numbers flying around, just like you see it in the movie it played. And then, after a few short seconds, well, nothing, of course. The app couldn't do anything. I remember verifying it to myself by putting one finger and then my nose and check if they have the same fingerprint. A couple of iPhones later, we did get a fingerprint sensor at the home button screen. And some Android devices even got under the screen fingerprint sensor, just like this stupid app actually predicted. In the meanwhile, I started my bachelor degrees at computer science. It was the obvious path for me. And it was around 2017 when it was time to choose the subject for my final project at the university, when Apple just introduced the new iPhone X with the new awesome Face ID. And I knew I had to dig around it. I knew I had to do it for that little child inside of me who tried to unlock his phone using his nose fingerprint. Today I want to take you all to that journey with me. We will start off by building a system just like Face ID. Then we understand it, we can try to break it. So let's look at it. The system seems pretty intuitive, right? All you have to do is take your phone out of your pocket, look at it, probably not as excited as this dude, and then some magic, some black box that you always assumed has to do something with deep learning, decides if to keep the phone locked or unlock it for you. Let's try to think how we can implement that system. We want to have a system that can scan the user face and create some sort of identification vector out of it. We need to identify it. That's why it's called Face ID. Well, we can think about a naive way to do it by using all sorts of features about the face, maybe stuff like the length of the nose, the width of the face, the skin color, and so on. We can use more complex stuff, maybe stuff like the ratio between the shade of the eye color and the shape of the lips. We will need to figure this out later and choose more features to work with. We usually choose 128 features. That's the magic number that the industry is working with. And now we have a good description of the face. We have something that identifies it. So we can save that identification vector inside a phone, and on the next day, when our users come again and want to unlock his phone, all we have to do is scan his face again, compare it to the scan from yesterday, and decide if to unlock the phone. The problem is working with faces can be a bit hard. Faces are always changing. We can take images from different poses in the different angles, in the different lightings. Our hair gets longer and then shorter when we take a haircut. Our eyes can get red and swollen after a sleepless night of coding. And even our nose can get longer over the year. So we need some strong solution here. That's why we need deep learning. We want a computer to solve that problem for us. But before we can talk more about deep learning, I want to give you here all intuition about how this stuff really works. So let's start off with something a bit more basic. Let's start with neural network. Don't worry, I won't bore you with math. And yeah, this is the stuff that is the base building block for everything we've seen in recent years in AI. But if babies can understand it, I'm sure so can you. The main idea here is we're trying to create some sort of a brain to our machine. We want to let the computer find some solution for us. This is not really how the human brain is working. Our brain is a bit more complex than that. But we took some ideas from the human brain, like neurons, for example. We have here some nodes, neurons if you will, containing some information. And by passing that information from one neuron to another and building a huge web of neurons, Our brain here can learn stuff and find some patterns and solve some problems. We order our neurons in layers. We've got ourselves the input layers here in blue and the output layer here in purple. The network is built in such a way that each neuron has some effect on all the neurons on the next layer. This effect can be a strong effect or a weak one, and it can be a positive effect or a negative one. This still doesn't make a lot of sense, so let's try to understand it a bit better with an example. Let's say you got a task. You want to identify if what you see in front of you is Python. No, not a programming language, but a real can kill you snake Python. So for this life-threatening task, you choose to use neural network. You got yourself two inputs. You can see the color of the snake, that's pretty obvious. And because the snake is coming through you with his mouth open, you can see the length of his teeth. So now we got ourselves the network, and we need to train it using examples we collected over the years. The network will adjust the weights, the connection between the neurons, until we got a network that looks a bit like this. This still doesn't make a lot of sense. But luckily, we as a developer has a secret, so you have to promise not to let it out of the room. We are really good at coming up with excuses of why our code succeeded. So let's try to find some reasoning here. We might say that the first neuron in the hidden layer, that's the name of the layer between the input and the output layer, is some sort of a poisonous detector. It's telling us how likely is that the snake in front of us is actually venomous. We can see there is a strong positive connection between the length of the teeth and the poisonous detector. That makes a lot of sense, right? We know that snakes inject their venom to their victim using their teeth. So longer teeth mean more likelihood of the snake being poisonous. We can also see there is some correlation between the color of the snake and the poisonous detector. Still make a lot of sense. If you imagine in your head right now a very poisonous snake, you probably see a really green, bright green snake in front of you. So that makes a lot of sense. We might say that the second neuron here is some sort of size indicator. It's telling us some information about the size of the snake. And that the third neuron is some sort of a pattern detector. It tells us if the snake has some patterns on it. So now, when our network tries to identify if what we see in front of us is Python or not, all it had to do is combine the different deduction together. If the snake in front of us is likely to be venomous, it's not likely to be Python. Python are not venomous snakes. On the other hand, if the snake in front of us is huge and has some cool patterns on it, it's probably a Python. I have some good news for you. Now that you know what deep learning is, now that you know what neural network is, you also know what deep learning is. Deep learning is just the idea of taking a neural network and adding more hidden layers in between. The more layers you got and neurons you got, you can go deeper inside your learning process and find more interesting, complex patterns inside your data. So you can solve more difficult problems. A known example for that is MNIS, where we try to identify which handwritten digit we see inside of an image. I took this awesome animation from the 3 Blue 1 Brown YouTube channel, and I really recommend to go to his channel if you want to learn more about the mathematics behind all of it. So we know what deep learning is, but we didn't really answer about how we can use it for face recognition. Luckily, we have another trick up our sleeves. We can work with a different architecture of a network. This is an encoder-decoder network. This is a different architecture of a network. It's sometimes also referred to as autoencoder network. The idea here is we're taking some information in big dimensionality, in this case 6 numbers, 1, 2, 3, 4, 5, 6, and the network is passing that information and we're getting the same information on the other side of it. We're getting back 1, 2, 3, 4, 5, 6. The trick of the network is that in the middle of it, we have a compressed layer, a layer with lower dimensionality. In this case, 3 numbers. Our network had to learn somehow how to compress the 6 numbers to only 3, and then how to decompress them to the original 6. It had to learn some patterns inside our data. Let's try to think of it from a different point of view. We want to work with images of faces. Well, images are actually a combination of a few million pixels. We also know from the old saying that a picture is worth 1,000 words, right? So let's think of it as somewhere in between. We have here 2 friends, 2 parts of the network that play in a game of charade. The first friend is some sort of a poet. It's trying to describe to us, using 1,000 words, it's write us a poem about the picture it just saw. The second friend is some sort of a painter. It's trying to recreate the original image just by reading that poem, that 1,000 words. So now they play in this game of charade until they get good enough in doing that on every image. They can recreate the image without ever seeing it. I like to think of it a bit like how the police can do sketch art. Imagine you've been a witness to a crime, and I hope you won't be. You just saw the face of the criminal in front of you, but you can draw it. You are a developer, not a painter. Luckily, by sitting together with the by sitting together with a police sketch artist, you can both achieve this goal. All you have to do is describe the most meaningful features about the criminal you just saw. So you start off by describing the hair of the criminal, maybe from a predefined set of hairstyles. Then you can describe his eyebrows. Then you describe his eyes and maybe some glasses if he had on. Then you can describe his nose and the mouth and the connection between the two. And the police have a portrait of a criminal and they can arrest John Lennon in this bizarre case. So let's do the same in our encoder-decoder network. We will train it to take an image of a face and return to us the same image from the other side. To be able to do it, the network had to learn some meaningful information about faces, meaningful features, so it can find out maybe stuff about noses, eyes, and mouth. We don't really know what the different features are because we never really trained the network to look for noses. But we do know we are getting a feature vector in the middle that it is describing the face. So now, we can break our network into two parts, the encoder and decoder, the poet and the painter. We don't really need a painter anymore. We don't care about recreating faces anymore. And we're left with an encoder network that can take an image of a face and return to us a feature vector that describes it. Okay, let's do a quick recap. If you lost me, now it's a good time to come back. We can now build a system just like Face ID. We can scan an image of our user here and pass that information through the encoder network. And we get in a feature vector that describes it. And we know it's a good description of that face because in some alternate reality where we still have access to the original decoder, we can generate this original image of you and only you just by looking at this feature vector. So with that system in hand, now we thought to ourselves, what could go wrong here? How can we break it? This is when this picture came into my life. You all probably seen this picture before. It's a face that was generated by a computer in a 2014 research. And it's supposed to represent the most generic, average white male face. We thought to ourselves, what does it mean that a face is really generic? What will it do to a system like ours when we provide it this face? So we started investigating it. We collected a lot of faces. We had a huge database of faces. Then we chose a smaller set of faces and we ran every face from the smaller set against every face in the big set. And we got some really interesting results. Most faces got exactly one hit. They were able to open exactly their own phone. Some faces got a bit more hits, between 2 and 4 hits per face. But this one face here at index 27 got more than 15 hits, which is insane. And you won't be surprised to learn that this is actually the generic face from before. So, with a strong hunch that something is going on in here, we started collecting a lot of information. We collected all the different feature vectors for all the different 10,000 faces we got. Then we ran some analysis tools over them, some complex mathematics model over them, and we got a different distribution of each of the features. We found out that most features are normally distributed, which might not make a lot of sense for you right now, but if you think about it a bit more, it makes a lot of sense. The network is probably taking the same shortcuts as we do as humans. When I try to identify one of my friends, I'm just looking at their noses, eyes, and beautiful smile, and I can identify them. So the network probably taking the same shortcuts. It's probably looking for stuff like noses, and if, for example, it chooses noses are normally distributed. The average nose size is 5 centimeters, or 2 inches if you don't believe in the metric system, Americans. And the average nose size is between 3 centimeters and 7 centimeters. It's very rare to see a nose longer than 7 centimeters. So we still don't really know what the different features are, but we now know the distribution of each one of them. We know the probability of getting each value here. So let's do a quick side note. A brute force attack is an attack where you try all the different combinations of a password until you get the right one. You start off by hitting 1111, 1112, 1113, and go on and on. In the case of a 4-digit passcode like this, you have 10,000 possible combinations. You can go with a slightly more sophisticated variant of that attack, where you start off by hitting the most common password, which is 1234. It's not exactly a dictionary. You start by hitting 1234, and you walk your way from the most common password to the least common password, the password with the most probability of getting hit to the least. So, what if we could do the same for faces? Well, we just saw the equivalent of 1234. It's this face from before. It's the generic face. It's the face with the most probabilities of getting hits. So we can do a brute force attack on faces. We can sample faces from the knowledge we just gained about the distribution of each of the features and sample the faces such that we're starting with the most common face, the most probable face, and we walk away to the least probable face. Now, all we have to do is just build the attack. As we said, we had an encoder-decoder network that was splitting into two parts. The original encoder is now gone. It's some sort of black box. And the original decoder, well, who remember it? So we had to switch things around and create a new network. In this new network, we take in as an input a feature vector, and we're generating an image of a face out of it. Then we pass it through the trained encoder and getting some sort of feature vector. And if everything went on correctly and our network did some good jobs, we're getting the same feature vector that we started with. Well, at the beginning, we got some shitty results. You can see here some random noisy image and some random numbers that correspond to it. But over time, our network got better and better in producing images of faces. At first, you can see here it's got the general shape of a face. Then it was able to composite the different features like eyes and noses. And it's got better in producing images of faces until it got to the point where we're generating an image of a face that when we provide it to the encoder not only thinks that this is a real face, but it thinks that this face is actually have the same feature vector that we started with. We can control now the attack vector. We can now control the input to the system. Okay, I promised you some shocking results at the beginning. Now it's the time to deliver, right? So we were able to get successful logins 13 times in a million attempts. Just one in every 100,000 attempts, on average, got successful login. It's just like guessing correctly, a 5-digit passcode. Here you can see the attack. Those faces won't fool you and me. We can tell that those are not real faces. But to the system, those faces not only looks real enough, they look like a really generic faces with very average attributes. So by generating thousands and millions of those and provide them to the system, we were able to get some successful logins. Now, if you stop on every of those faces for more than 1 second, you can probably see someone you know in them, because again, those faces are really generic. So maybe it's the person next to you, or behind you, or your best friend. So we got to the sad conclusion that no one is safe. Well, I have a couple of disclaimers about it. First of all, it's important to say that this was an educational-only research. We ran it inside the university in a system that provided to us by the university. We attacked faces that signed an agreement to allow us to do it, and it was really nice. But we never really ran against Face ID. We don't really know if Face ID is actually working exactly the same way as I just described to you. Nobody ever disclosed it, so we don't really know if it's working exactly the same. And Face ID comes with some complementary system, like blocking you out after 5 failed attempts. So it was too much of a hassle and not really the point. Another thing that is important to say is that we ran this entire research back in 2017, meaning we didn't have access to all the latest models we have nowadays in AI. And we all know how quickly this field moves nowadays. So they probably got a bit better and more secure over time. On the other side of the same coin, we ran this entire research back in 2017, meaning we didn't have access to all the latest models. And nowadays, we know a lot more about generative AI and deepfakes, and we can probably generate even better looking faces that can fool the most sophisticated system they have today. One last point I would like to make, and this is a question I'm getting a lot, is what about 3D images? Because we all know that the original Face ID is working with a 3D camera. Well, we believe we can fool those systems as well by doing some tweaking to our system. If you think about it, the system doesn't really care about the raw information, the 3D information it's getting from the camera. It's only cared about the compressed information we're getting from the encoder. So we believe we can generate 2D images that will correspond to the same feature vector that a 3D image will. And this way we can fool those systems as well. Thank you very much. I hope you learned something new today. In this cringy animation, you can see me and my partner in crime in this research, Roy. Yeah, we are both named Roy. And feel free to come by later with any question or just send me a mail. Thank you very much.